The broadcast is now starting in listen-only mode.
Good afternoon, ladies and gentlemen. Welcome to TechGig webinar series, our endeavor to empower techies. We believe that sharing of knowledge is the key to enhance our skills and grow us as professionals. With this principle in mind, we have initiated a series of webinars conducted by industry experts to give you all a crisp insight of various domains. The topic of today's session is Conquer Unprecedented Complexity by Making Better Use of Engineering Data. Our guest speaker today is Vivek Jayakrishnan, Senior Software Engineer at IBM India Private Limited. He is currently working as Senior Software Engineer in Rational Engineering Lifecycle Manager Development Team in India. So without further delay, I introduce you all to our guest speaker. Over to you, Vivek.
Thanks, Aradhana. Okay. Okay. Hi all. Thanks for sparing time from your busy schedule to attend this webinar. I thank Aradhana for hosting this and the TechGig team. So without much ado, I start off with my presentation. So the title of this presentation is Conquer Unprecedented Complexity by Making Better Use of Your Engineering Data. It seems like a large, long sentence, and my goal is to spend a couple of slides trying to understand what do I refer to as complexity here, what do I refer to as engineering data here, and what are we trying to conquer. So I move to the next slide now. Aradhana, is the slide up and running?
We can see the slide of Smarter Product Rising Complexity. You can please proceed.
Yes. Yes, thanks, Aradhana. So as we all know, in today's engineering environments, organizations are actually aspiring to innovate and are building even more complex products and systems to actually differentiate themselves. Now, if you think one level deep, you will find out that the associated engineering effort is actually generating more and more data with ever-increasing complexity. When I talk about engineering, I would rather term it as a broad software and systems engineering together. The entire software and systems engineering effort is actually generating much more data, and the complexity of that data is also increasing. Speaking with customers, we have seen a couple of trends which is happening in various industries. One trend is that we see more software and systems of systems design being incorporated, particularly where a large portion of the product or the value or the innovation which is being delivered in that product is via the software. We can also see a lot of design and development artifacts actually being generated much more frequently than it used to be in earlier days. With the advent of agile practices and DevOps integrations and continuous integration, continuous delivery, just-in-time supply chain, we can see that the amount of artifacts are actually having much more frequency of development. We can also see that companies are actually thinking in terms of product variants. We can see an ever-rising collaboration between hardware and software teams. We can also see in the industries that there are a lot of participants in the supply chain, not only in the electronic, the hardware or the mechanical supply chain, but also in the software supply chain. to add to all this, all of us are again bound by constraints. So all of us are required to do more with less. All of us are required to improve quality. All of us are required to improve productivity. And of course, there is more pressure to get to the market faster. So with these points, it makes it a bit clear that smarter products and the way we actually do our engineering using all the smarter techniques is actually increasing the complexity of this effort. So this the notion of complexity is a notion which I would like to actually delve deeper as we proceed along the presentation. My next slide actually talks about, or would like to talk about, how complexity actually impacts an engineer. When I say engineer, I'm actually talking about various roles in the software and systems engineering approach. Not necessarily a systems engineer, but the person could be a software engineer, a hardware engineer, a developer, a test engineer, a program manager, a product manager, or even a C-suite executive. So I'm trying to understand, or I'm trying to actually capture my thoughts on how this complexity actually impacts the productivity. So the statement which I want to make is that in this environment of increasing complexity, for engineers, the day-to-day tasks can actually end up consuming an inordinate amount of time, which I feel could have better been spent with them being creative and productive. So questions like those that are seen in the chart are often posed to most of us. And I'm sure that most of the people in this webinar would be having to deal with such questions on a day-to-day basis. The questions are often difficult to answer. Not only are they difficult to answer, providing answers in a timely manner is also very important. Now, for example, let us look at one question which a product manager might have. The product manager might be thinking about a new phone, a new smartphone to be launched in India. And he must be thinking, okay, I know that the smartphone was actually modeled in US, some changes for the Indian market before we actually start developing the smartphone. Now, in the first place, he would be running around to figure out what does my smartphone in the US look like? What are those engineering artifacts which went into defining a US variant of the smartphone? Only once he understands, or he is having control over what are the artifacts which define the US variant, can actually he think about defining a new variant for India or for any other geography or any other need. There could be other people in the organization. For example, a test manager. The test manager might be working in a critical healthcare medical electronics company, and they might be developing heart monitors, and he really wants to make sure that he knows for sure that there are not many requirements for the heart monitor which have failed in the last execution run, because everybody knows it's like safety critical device. So he needs to know how many requirements for the heart monitor are related to the tests and how many of them have failed on their last execution run. Now, there could be many such questions which actually come up, and teams actually need information in a particular context at their fingertips to be productive and to make good engineering and business decisions. Now, this data typically in organizations reside in many locations, many repositories, if I could use that term, and pulling that all together, a lot of time, effort, and it's prone to errors. We have heard a lot of engineering organizations tell us that they face challenges like it takes a far long time for us to find information we need, especially when the information is stored in multiple places. And oftentimes we miss some information, and that creates rework. That has been the feedback which we got from many of our customers. A few of them have come up and explained to us it's really getting difficult to understand the impact of changes which is happening across multiple engineering disciplines, versions, variants, and products. It's getting impossible to get a quick at-a-glance view of the real-time status of the life cycle of where each product is. We have had other customers who have come and talked about how they don't have an effective way of sort of rapidly defining new products, versions, and variants, and reusing from and learning from previous development. And they have a challenge which is a time to market challenge. So all these thoughts together is reinforcing the belief that our way of working and our way of working on smarter technologies, developing smarter products, working in smarter environments, working as smarter teams is actually increasing the complexity. And this complexity is actually affecting the engineer's productivity. To give some details on the effect of productivity, I'm looking at multiple pillars now. The first pillar I would like to look at is the pillar of time. So my next slide hopes to try to recollect a study which was actually performed by IDC, and trying to explain the impact of this complexity and on time. Okay, so there was a study which was conducted by the IDC group, and they worked with a lot of organizations like the Working Council of CIOs and Reuters and a lot of management associations. And the goal was actually to determine how much time do actually engineers or knowledge workers in this study spend trying to find information. There was a lot of interesting statistics, and I feel that most of you would agree and nod to these numbers. For example, one of the numbers was that knowledge workers actually spend 15 to 35% of their time just searching for information. Now, knowledge workers are a broad category, but we could definitely apply the same dynamic and say that it affects and afflicts engineers and engineering data also. So definitely we can use the statement engineers spend 15 to 35% of their time searching for information from their engineering data. That is a pretty substantial amount of their valuable time. Well, that is a startling statistics in this slide deck, which talks about how 90% of the time knowledge workers spent in creating new reports, and most of them is actually recreating information that already exists. I can visualize a lot of nods in this room wherein we really understand that we spend a lot of time in creating reports, which are becoming more and more necessary. Working as globally distributed teams, we really need to make sure that our status is up to date, our dashboards are up to date, our operating reports are all green, our operating reports are truly representing the latest status. So it's startling to understand that 90% of the time we are actually trying to work with data and information which is already existing. So overall, the estimate is that a knowledge worker or an engineer spends a day a week searching for data and then reformatting data or extracting, transferring, and loading that data in a way in which he can actually make good value out of that data. So this slide predominantly was to try to talk about how the complexity in data is actually affecting the time pillar. Now I actually wanted to move focus on the next slide to what I call as the cost pillar. Now taking a similar study was actually done again, taking data from the research I just mentioned now, and using a hypothetical cost to a product development organization of 100 engineers, assuming that the annual cost per engineer is $150K. There was some detailed study done in the breakup of task which these engineers actually did most of their times. So the predominant and impact analysis and coverage. So I'll just spend a few minutes trying to explain what this search means. So this search actually covers both simple text searches across the distributed data sources, which they would be using for the engineering. For example, text searches against their requirement gathering tool, text searches against their defect repository, text searches against their test case repository, test searches against their source code control tool, text searches against their modeling tool, their work item tool, their project planning tool, just trying to search. And it also covers complex searches. For example, find all the requirements and test cases and work items and design elements that include the term, say, handset. Or for that matter, deriving from an earlier example, a complex query like how many requirements for the heart pulse monitor are related to the tests that fail on the last execution run. So these are the sort of searches which typically people are trying to achieve from their engineering data. And that is supposed to take around 15% of their time. The second bullet is on how creating documents. Actually, this talks about how we try to pull together integrated reports from multiple sources. All our sources together, might be it's a traceability report, it could be a coverage report, it could be an impact analysis report, it could be a safety report, it could be a compliance report. And to pull out data for creating such reports, we need to actually look at multiple sources. The multiple sources which actually store and manage and provide a life cycle to various components of your development life cycle, not only for software, for your systems as well as hardware. That is supposed to take around 5% of the time, and 5% of the time as well as a dollar number to that. The third and important aspect is about impact and coverage analysis. Impact and coverage analysis is like picking a focus point, say a particular artifact, and seeing all its relation to other artifacts in order to determine the impact of a change to that artifact which you have focused, or to check that there are relationships to other artifacts to verify coverage. For example, does the requirement have a related test case associated to it, or does if I change a particular requirement, what test cases would need to be changed, what design elements need to be changed, what of course are the hardware changes, what of course are the software code changes. So it's very important to stress that the impact here, even though it is being quantified, the impact can be far greater than the quantified costs on the slide. Actually, missed information in actually searching impacts a lot. For example, we need to change some properties of a number of requirements for response time of various systems functions. So we search, but we don't find them all, and so we miss changing the response time for a particular function. Now, hardware and software is designed and implemented, the system is delivered, and then function responds outside the parameters we really wanted. So this would result in a high cost of rework or even product recalls, which we have seen a lot in the industry. Similarly, if an area of the product is missed when performing what we call as impact analysis, then the cost and effort of implementing a change request may be incorrectly assessed, and worse still, the change request may not have been fully implemented at all, again leading to rework costs, possibly leading to late delivery, and again worse, leading to product recalls. Basically, the resulting costs can be pretty huge. So what's really needed is a way to enable engineering teams to focus more on the core engineering work and spend less time and effort in dealing with complexity and rework. We actually have to restore the balance and help engineering teams to work faster with higher quality by improving their development processes and asking the tools to do more, right? So basically, we need a next generation approach to both the processes and the applications or tools that support these processes. So with this context in place, I would like to take this discussion to the next part, and this part talks about how we are all working as in smarter teams, working on smarter products which have not been developed the same old way. So this is sort of the third pillar or the third challenge which most of us are actually facing. So traditional product development was sort of linear, like 10 years before today. The product development was linear. When I say linear, I mean it was led by basically physical and mechanical engineering disciplines, if I could use that term, and with teams in one place and with sort of limited upfront planning. But actually the development of the next generation of products and systems demands a sort of a top-down holistic approach, and most of these places it's the software which is driving the innovation. And since most of the places it's the software which drives the innovation, these products must be actually developed seeing how the software and systems interact with all the other areas upfront, sometimes even before development begins. So basically, software is no longer secondary, actually. It is actually upfront. Thus, a systems engineering approach is sort of becoming encore and in focus rather than trying to do a traditional physical bill of materials based approach and rather view it as a bottoms up assembly of parts. So basically the solution here is to look at it as a top-down holistic and a domain integrated approach rather than a bottoms up assembly of parts. So definitely all of us are working on next generation products, and hence a next generation approach is needed. So having discussed the implications of complexity, the implications of the complexity of engineering data across the three pillars of time, cost, and traditional way as well as the current way of working, I would now focus on the next part of the presentation, which is to understand how we propose to solve this problem. So all of us have actually worked in organizations wherein we must be having lot of data across various uh, activities which we do in developing systems and software projects. For example, we must be using a particular tool from a particular vendor for requirements. For planning, we might be using a different vendor or the same vendor, a different tool. We might be dealing with electronic and electrical components. Of course, most of us deal with source code. A few of us also deal with mechanical parts. Predominantly, all of us need a way to manage documentation. And so we have understanding that traditionally, much of the data that we created and managed during this entire life cycle of the systems and software projects is actually not open data. Historically, this data has only been available to users of the tool that manages that data. You might be using a tool to manage your requirements, and that data, those requirements historically may have been only available to the users of the tools of that requirement tool and to manage that data. So in such closed environments, we are actually prevented from answering complex questions that actually rely on our understanding of the relationships between the data managed by the different tools. For example, the requirements which are linked to the test cases, or the requirements linked to the models, and the models which are linked to the test cases, and the test cases which are linked to a particular source code. So a closed environment, and we are sort of prevented from answering complex questions. Furthermore, many times the tools in such closed environments have less common understanding of the types of data and relationships that they are trying to manage of the other tool. So I agree, the problem is not new, and it has been attempted to be addressed in several different ways in the past. For example, using a single repository has been a way to manage all this data, but pretty much it has turned out to be sort of unrealistic, since it implies that a single vendor is required. A single vendor needs to be made sure that he or the vendor understands the entire spectrum of this data. And what happens is this prevents the adoption of the sort of the best of breed solutions, and it becomes a pain of integrating of data that companies have in their existing repositories. It's simply not practical also to migrate all your data. I want to introduce a term here, all your life cycle data into a single monolithic repository. First of all, we might be having terabytes and petabytes of such data, and such repositories have actually huge operational challenges with their performance sizes, their upgrades, and their backup. So this has been traditionally a failed approach, wherein we try to look at it as a single repository problem. The next stage of evolution was the sort of the point-to-point integration between multiple tools. That has resulted in something which has taken us to the next level of challenges. It did help solve the challenges which happened with the single repository approach, with the point-to-point integration approach, but the point-to-point integration sort of proved to be brittle most of the times, and also prone to breaking when the tool versions are sort of updated. In the hardware, in the electrical and electronic industry, there has been a lot of focus on trying to build up universal metadata standards. History has showed us that there has been a 50% success here, and predominantly sometimes due to conflicting priorities and motivations between multiple vendors, and coupled with the fact that the standards were sort of very rigid and were not providing any flexibility for the individual teams to customize, that approach has also not sort of kicked in, if I could use the word. So traditionally, a single repository approach to actually find a repository which can be act as a single point of truth has actually not succeeded. So what can we do for this? So my next slide talks about how smarter development needs smarter ways of working, right? So this slide talks about how within IBM and within Rational, we have tried to develop a methodology, a way of smarter development using an internet-inspired architecture. So with the assumption that the linked data concept is pretty familiar to all the participants, I'll try to summarize linked data in a nutshell. So linked data, according to me, is a phrase that actually refers to a set of best practices for establishing a web of data. That's all. So the linked data need to be read by machines, and they need to have some explicitly defined meaning. They should be linked to other data, and they can in turn be linked to data from other places also. For example, other data can actually link to this data. So basically the founding principles of linked data has 4 supporting principles. First of all, use URIs or uniform resource identifiers to identify things. Then use HTTP URIs or the hypertext transfer protocol URIs so that you can dereference and look up those things. Okay, so when someone dereferences or looks up a URI, we should provide some useful information about what we are trying to explain in that URI. And as part of that useful information, we actually include links to other URIs so that additional related things can be also discovered. Now, this is something which is pretty ubiquitous in our generation, and this is the World Wide Web. So just as the World Wide Web relies on uniform resource identifiers and HTTP protocol to provide a huge scalable architecture for linking documents, say your HTML pages, regardless of where those documents are physically located, it actually uses the same underpinning technology stack to provide the same scalability for linking the structured data. So regardless of where the data is located. So we are trying to actually bring and adopt the technology which is prevalent in the World Wide Web to provide the same scalability for linking sort of structured data. And the structured data are your engineering data, which has a particular structure to it, but in various disparate repositories and which are not linked with each other. So regardless of where that data is located, we are trying to use this technology of the World Wide Web to provide the same scalability for linking structured data. So adopting a loosely coupled approach to integration based on these linked data principles in our systems and software development actually allows us to truly make the most of the data that has been created without the downsides of all the approaches which I explained in the previous slide. So we have been able to derive huge benefits from applying this linked data principles to the engineering data we have. By actually opening the data managed by all of the tools which we use for our engineering, we can actually create a well-defined system of tools that allow users working within any of the tools in that entire organization or system to answer complex queries about the products or the projects that they're working on, and which basically rely on the union of data which is held in the other disparate repositories. So the focus has been to actually leverage the World Wide Web to develop a more scalable, open, flexible integration technology, which we could call as an internet-inspired architecture to actually better help us answer our complex questions with which we have for our engineering data. Having said this in mind, the questions would be, how do these tools, how can tools adopt the underlying World Wide Web mechanism of linked data? There has been a community approach to this on the called the OSLC, Open Services for Lifecycle Collaboration. So this has been a participative open community, more than 100+ companies in the lifecycle tools domain, wherein there has been a lot of formats being suggested by the OSLC work groups. Say for example, you are either a vendor of a change management tool, or you are a user of a change management tool, or you are a vendor or user of a requirements management tool, or a user of a requirements management tool, or for that matter you are a vendor or a user of a CRM tool. There are a lot of OSLC defined formats for each of these domains, or many more domains in this life cycle, in this engineering life cycle. So the power of OSLC is that there are a lot of core formats, and if there is no sort of, you find yourself, if your tool which you are developing or the tool which you are using is a homegrown tool, and you seem that it is not part of any appropriate OSLC domain, you can actually create your own vocabulary, and you just need to define that vocabulary in an RDF representation. So RDF representation is the resource description format representation, and it's pretty simple, straightforward representation. And you just need to make sure that the RDF representation, in that RDF representation, you are covering whatever you want to pass to the other tools to consume your data. So they would just look at your tool. Say for example, you have a homegrown tool for defect tracking, and you want to actually link to a off the cards, a commercially off the shelf tool by vendor A, and you want to link with that tool. So the only thing which you need to make sure is that when the tool from that vendor is actually a consumer of a particular format, and that you define your representation and your vocabulary of what data and services which your tool provides in the OSLC format as an RDF representation. And definitely the vendor's tool can easily integrate with your tool without actually moving data. Your users can continue to use the tools which are there in your homegrown tools. No need to move data, but your customers or other users, end users, would still be able to leverage disparate tools. So this is how we actually think about getting the RDF data in OSLC formats. Now, definitely the question is, okay, now we understood that we have this concept of link lifecycle data, linked data concept, and the concept is that we can use OSLC integrations to establish integrations between this linked data. So it becomes really easy for practitioners and engineers working in their day-to-day tools to see what other things their artifacts are directly linked to. For example, I said, the quality engineer can easily see the requirements that are linked from his or her test cases or defects. Pretty decent. With OSLC, we are able to achieve that. But it's more difficult to actually answer engineering questions that span the entire life cycle. For example, questions like which requirements, model elements, and tests contain the word cruise control. Wouldn't that be difficult to look at and answer that question? Or for example, a safety standard has changed in my organization or in the industry in which I am developing this product for, which requirements, design elements, implementation artifacts are impacted by this change in the safety standard. Now, this is still a tough question to ask because this question actually spans the entire life cycle, which involves multiple tools and not just two tools. So, but we can solve this problem by actually creating an index of the linked lifecycle data. So we have tools, we have data, we can get to make them link with other data using OSLC prescribed formats. And now, if we could push this link information to an index, which is updated in real time and it reflects the changes ongoing in all the underlying engineering tools, then this index would support us asking questions or querying across data from the entire life cycle in real time. Within IBM, we call this index the lifecycle query engine. The lifecycle query engine is one of the key innovations which is propelling a product called the Rational Engineering Lifecycle Manager. In the next slide, I would actually begin my topic of actually introducing the Rational Engineering Lifecycle Manager. So, just recapping what we went through. So I discussed how smarter products, smarter ways of working, smarter teams are actually leading to increase in complexity. This increase in complexity is actually how it is actually affecting the day-to-day working of an engineer. Again, I'm reiterating the fact, when I say engineer, I'm just generalizing the role or the various roles across the engineering organization. I also explained how we have seen the effect of complexity on time, the effect of complexity on cost, and also the new ways of working, how is that being affected by complexity. I spoke about the of linked data. I did speak about the OSLC specification and how we can get our products to link with other products, other disparate products. Now, and I talked about the lifecycle query engine and how we can use the lifecycle query engine to actually aggregate and link all this data. Now, RELM, the short form for Rational Engineering Lifecycle Manager, is actually built on top of this lifecycle query engine, and it actually extends the rational solution for systems and software engineering. So this RELM makes available multidimensional views of your engineering data, and thereby enabling your multidisciplinary engineering teams to be more productive and make better decisions. Like I said, RELM's key innovation is the use of the lifecycle query engine to index all the linked data from many engineering repositories, which further makes it possible to mine it in new different ways in real time. Also, the fact that the data is federated rather than synchronized or stored in one monolithic database means that it is possible to implement the solution much quicker and with a finite ongoing maintenance effort, which is of course less true of all the alternative approaches which we have discussed. So RELM is capable of indexing data from the tools of the rational solution for systems and software engineering. Plus it has the potential to index third-party and homegrown repositories which require just development of lightweight connectors for each of these repositories. So as of the current release of RELM, the first release of RELM was in 2012, third quarter 2012, and we have been able to make different strides. The initial release actually was capable of indexing data from the tools of the entire Rational family, Rational Team Concert, Rational Functional Tester, Rational Quality Manager, Rational Design Manager, Rational Software Architect, Rational Team Concert, many tools. And over the last year, we have been able to index third-party tools like HP Quality Center, open source tools like Bugzilla, and also homegrown repositories. Of course, these integrations would require lightweight connectors to be developed for each of these repositories. If these repositories are from participating organizations and companies in the OSLC ecosystem, the effort is incremental. So RELM includes an application actually which runs on what we call as a Jazz Team server, and this provides access to the data through your web browser. So in fact, it's a web-based application. So the three main concepts in RELM is that this product provides you, your team, new ways to visualize, analyze, and organize your engineering data so that you can get new value from it. So I'll just spend brief time on what I explained by what do you mean by visualizing, what I mean by analysis, and what I mean by excuse me, organizing. So visualization capabilities allow you to set up custom views that are populated with real-time, near real-time data to provide, say, new perspectives that would help your team make decisions and perform tasks. For example, an automotive engineer wants to view a view of all the cross lifecycle data in the context of a particular standard, for example, the ISO 26262 standard. So he can actually visualize that by developing a custom view, which will be populated with all the data coming from each of the tools with near real-time indexing happening, and he would be able to layer or overlay it across any of the visualizing capabilities he wants to do. For example, an automotive engineer would want to understand all the lifecycle data overlaid on a picture of a car with data shown over the parts of the car to which it relates to. For example, the collision system. In the collision system of the car, what all artifacts are actually being used to develop the collision system of the car. So you can actually overlay this data on a picture of a car, on a collision system of a car, and sort of get a visual representation of what are the requirement artifacts which were used to develop this collision system, anti-collision system in the car. What was the sort of the change management and configuration management, version control artifacts which were used. What was the design artifacts which were used, what was the modeling artifacts, what was the test cases which were used. So he could get a consolidated view using the visualizing capability of RELM. Using the analysis capability, the analysis capability helps in team-oriented analysis, for example, across disciplines, and it would help teams quickly find relevant information and quickly identify the dependencies that they may otherwise have missed out, which could have been in the downstream components which they are using or which they are getting from their suppliers. For example, with RELM, searching for all engineering artifacts across multiple repositories, multiple tools containing the phrase fuel pump becomes a simple and quick and error-free task. Or perhaps, say, a supplier, you find out that a supplier can no longer supply a particular electronic component, and you need now to determine what impact there would be by switching that component from for a similar component from another supplier. What is the impact of switching a component? So now, in the context of switching the component, you will need to understand the potential impact on component interfaces, right? with the software, and actually with the software that controls it also. This would typically mean asking multiple teams to perform impact analysis in different tools and then assembling the data, right? You might ask your hardware team to bring out the impact from the hardware side. You would ask their operations team to bring up the impact from the operations side. You would be actually asking the software team to actually bring out the questions, the answers to the questions from their side. With RELM, you can find the component in your system design and generate an interactive impact analysis view that will show you all the other systems and software design elements and requirements and test cases and work items associated with that component, provided this information is available in the index. So provided that the tool has been instrumented to participate in the index. Now you can work with the view to filter out any artifacts that are not relevant and parcel out relevant branches to the relevant engineering disciplines to analyze. So RELM actually offers potential for better reporting also from this wealth of data. Answering to complex engineering questions can be visualized and displayed in the most appropriate way for the task. And documents can be generated containing data from across the life cycle to support audits, providing compliance, specification delivery, or specifications that form basis of contractual agreements across your supply chain. This would actually give us a lot of benefits and substantial reduction in the effort which you would be spending to look at this data and arrive at information. The next couple of slides I would go through typical use cases in RELM. The first use case, like I explained, was the visualizing, navigation and exploring use case. I will try to be quicker so that I have some time for questions. So for example, the typical use case is so that I can more easily achieve and monitor a compliance to a safety standard as a safety manager. I need a view that shows me the different processes, tasks, their status, and the related tasks. So now I have some screenshots captured, and you will see that most of these views are actually very real-time, and they are very dynamic views. They are real-time dynamic views, and you can interactively explore them and interrogate them, and you can actually get more information out of them, and everything is sort of real time. And you will look that they are spanning the entire life cycle of information, the test cases, your design models, your requirements breakdown, and these are all views which are live. For example, any change which happens in each of these tools which actually you are using for test cases, if a status of a test case change, in near real time it gets updated into this view. So you can create a lot of these interactive views. You can create it in various tables, grids, and trees, and free-form forms, and you can also layer them over your standard views, and process standard and framework-centric views are also possible. I go to the next slide, waiting for it to load, and here we talk about how we can search and query. So like I explained to you, the lifecycle query engine is based on the RDF technology, very scalable. We can store billions of artifacts, scalable to billions, very easy schema. RDF also exposes a query language called SparkQL, very good triple store technology to use for data mining and other operations. So you can actually execute search and query to sort of analyze and understand what's the overall implementation status, or perform some plain text searches across all this development lifecycle data. You can construct even powerful queries to answer certain specific questions you might have on the products which you are under development or test or design. I will move on to the impact and coverage analysis, which I feel is one of the most crucial aspects of this, which I explained in the past also. So the example user story is so that we can understand the impact of a change to a safety requirement or a product for different markets. For example, what if a safety requirement changes? What are the relationships? What are the downstream components which get impacted by it? What are the upstream components which are impacted by this safety change? Discover which products, systems, subsystems, components, their versions and variants are also getting impacted by this change. This is something very, very important for line of business executives, for product managers, even for test managers to really understand where should they focus their testing to be done. For technical leads to understand what requirement has changed and which code now I need to change. Just to understand the impact is a very powerful thing to have. And last but not the least, I would shift my attention to document generation. We're all living in a world wherein we have to adhere to a lot of standards, processes, industry-specific frameworks, compliance audits. So it's so easy now to actually create documentation and create documentation which can include data from across your tool. No more running ETL jobs on your data warehouse. It's almost real-time data which is available in your index. You can just go and you can automate the creation of these reports. You can use predefined document templates and specific industry templates and generate the reports. And so it's so easy, so real-time, and very easy to use. So with that, I actually end my presentation. I have one more point to cover, and that is about organizing the engineering data. And this could be a new concept, but the concept of organizing individual data is to actually provide all the engineering data a context. For example, you are developing a new model of your smartphone for India for the year 2014, which needs to be released in the first quarter of 2014 and which needs to be within the sub 10,000 rupee budget. So that is a particular context, right? You would like to really organize and structure your engineering data, all your engineering data within this particular context. So RELM also provides a aspect of providing a context for actually visualizing and rendering this entire data, all the data, your queries, reports, your impact analysis, everything. You can organize it properly within a particular structure which you want to define, and then you can reuse that structure. You can create variants of that structure. You can create branches of that structure. With that, what happens is all this data is encapsulated in one particular structure, and you can reuse across your various project lines. So with that, I would open up for questions. Aradhana,
Yes, Vivek,
do you have any
time,
questions?
yes, due to time constraint, I request you to take couple of questions that I have provided you before concluding today's session. So you will find the questions in the questions doc. Can you see them?
Sure. Yeah. So I do see questions. I can answer one question straight away. So the question is from Shreyas Sanjay Kulkarni, and his question was, can we use data warehousing and data mining techniques to conquer data? I am hoping that Shreyas has found an answer. Yes, we can use data warehousing techniques, but if you use data warehousing techniques, you need to go through the painful job of ETL, basically extract, transform, and load that data. The moment you talk about extracting, transforming, and loading that data, you make that data sort of dated. In this concept, we do not have the data coming out for a data warehouse where you need to extract, transform, and load, but you can actually apply all your data mining techniques directly on near real-time data and not having to focus on doing your extract, transform, and load operation. It is a very pertinent question. The power of RELM is that you can now you have all this linked data available near real time. So all your data mining techniques, all your clustering techniques, all your algorithms, all your machine learning algorithms can be applied on real time data using RELM.
All right, I think we are running short of time. So if you can provide some concluding lines before closing this session.
Okay. I would like to just take this opportunity to actually expose you to a YouTube channel. It's the IBM Rational User Education channel. Within YouTube, you can just search for Rational Engineering Lifecycle Management or Rational Engineering Lifecycle Manager, and you would see a lot of videos on how our customers are actually using these tools, videos on how you can leverage and benefit from each of the overview use cases which I gave to you. You can also go through our website in jazz.net or find more information within IBM website. You can also reach out to Rational IBM support. They have a specific channel in Facebook, in Twitter, on your social media network of your choice. That's it, Aradhana, from my side.
Okay, Vivek, due to time constraint, I request you to take the unanswered questions offline, which I will share with you through email. And I'm really thankful to our guest for conducting this wonderful webinar. It was indeed a great session. I would also like to thank all our participants for their support in making this webinar a success. The recording of this webinar will be available on techgig.com by tomorrow. Thank you all for joining us today. Thank you, Vivek, for taking the time out for today's webinar.
It was my pleasure. Thank you all.
All right, Vivek. Bye for now.
Bye.